Okay, so welcome everyone. So to all the students who are involved in this work experience week, it's wonderful to see you here. It's just a real shame that we're not all together in person in our building, but I hope you can have a really positive experience this week. I am very happy that you were in the hands of a very safe team who will be looking after you. They've done this many times before, and they put a lot of effort into making this a very special week for everyone that's involved. So I'm Phil James, so I'm the head of the Astrophysics Research Institute at Liverpool John Moores. I've not been doing it for very long. I just took over at the start of last year, so I just got my feet under the table, as it were, when the coronavirus hit, and so I've done the job mostly from my home, working remotely. But it's a position I'm very proud of, I have to say. I'm absolutely delighted to be the head of this wonderful institute in this great university in a wonderful city. So we're a pretty large astrophysics research institute. We have about 100 members of staff and PhD students. So about a third of that 100 are studying for PhDs with us. And I'll just start with the big question. So what does an astrophysics research institute actually do? And it sounds like it might be a very complicated answer, but I try and make it as simple as possible. I think we do two things. We find out new things about the universe and we tell people about it. So that the second is equally important. There's no point finding new exciting things about the universe if you just keep it to yourself. So a large part of what we do is communicating with other people. One of the ways in which you find out new things instantly is by talking to other people as well. We don't just do it for ourselves. We're part of a large community, so we have to communicate all the time. It's a flow of information both ways. Communication is all important, and as Andy has already said, asking questions and not assuming you know answers to things is always very important. So the things, going to the first of those two aspects, finding out new things about the universe, we're pretty broad-based, which keeps things very interesting here in Liverpool. So we look at lots of different areas of the universe. So we look at things all the way from stars and the disks around young stars where planets can form on the smaller scales, all the way up to galaxies and structures of galaxies and the whole cosmos. And we do that both observationally, and I'll say a little bit later about the particular way we have of observing the universe, which is unique to us in Liverpool. But we use big telescopes all around the world to make observations of the universe, everything, planets, stars, galaxies, galaxy clusters, and the whole universe. But we also have a big group that's involved in one of the other main areas of studying the universe, which is through computer simulations. So we have a cosmological simulations group, which is one of the best in the world, and they use extremely powerful computers to simulate the whole universe, and they're remarkably successful at that now. They can produce really detailed properties of galaxies, which are the things I love and have spent most of my career working on, within their computers, and can now look at really detailed comparisons between the computer simulations and what we actually see out in the universe. So astronomy instrumentation, this is part of operating our own telescope, the Liverpool telescope. I'll say a little bit more later, and Andy will go into details on that. Galaxy evolution and cosmology, I've already mentioned, through observations and simulations. Now, transients, you may not know what that means. Basically, this is anything that changes on short timescales, and this is something that we're very interested here in Liverpool. Again, ties in with our own Liverpool telescope. But these are things like exploding stars, so novae and supernovae. The most energetic stellar explosions are things called gamma ray bursts. So we have a big group that's expert in those things. And things like eclipsing stars and variable stars. And again, these are things which are very useful for observing with our own Liverpool telescope. The other aspect of transient science at the moment is that this is the main area in which I think we're getting the benefits from multiple probes of the universe. So not just using normal light, but looking at different wavelengths of light, different particles. So for example, detecting neutrinos. And the big, really, really exciting area that's developed over the last 5 years or so is using gravitational waves, where very dense objects are merging together, giving out gravitational waves and looking at the signals that come from those. And that's telling us huge amounts about really exciting things like black holes, for example. And that's all part of what we call transient astronomy. Star formation and evolution, how stars and galaxies get to be the way they are, is another major area of our study here. And again, that's both the observations and from the simulations. And finally, a term you won't have seen anywhere else, I don't think, because it's an area that's quite largely been pioneered here at Liverpool by my colleague Steve Longmore and people working with him, astroecology. This is actually applying techniques that astronomers use to big questions in things like loss of species here on Earth and climate change. And so a lot of it involves using drones and drone technology, but using the software that have been developed for studying, for example, big samples of stars and galaxies in the universe, turning that back and looking at the Earth and looking at addressing problems here on Earth using those techniques. Second slide, please, if whoever's in charge of that. Right, thank you very much. So how do we do all this? Teaching, we're quite unusual in Liverpool John Moores University that we have a big astrophysics group, but we're not part of a physics department. So astrophysics is a subset of physics. So basically to do what we're doing, all of us researchers have a good deal of training in maths and physics, but we're not part of a physics department. So to do our undergraduate teaching, a lot of that is in collaboration with the University of Liverpool Physics Department, and that's an association we've had going since 1998. Sorry, I should have said that the whole institute has been going since 1992. So we're coming up to 30 years old. So a few years after we formed, then we founded this association with the University of Liverpool. Doing research, that's basically down to the permanent researchers, so the lecturers and professors in our department, but the absolute core of powering that research is our big team of PhD students. They're at the heart of our research, and so PhD students are very important to us here. We operate and maintain the world's largest robotic telescope, so that's the image here, the Liverpool telescope, and I'll leave Andy to tell you more detail about that, but that is what is powering the research that we do in the transient universe. So it's basically a very flexible telescope that can pick up on things that change on short time scales. So stellar explosions, things that change very quickly. Part of our program of communicating with what we find with the outside world is the National Schools Observatory. So a lot of the people who are on this call today who have organized this Work Experience Week are part of our National Schools Observatory program. Also, as part of our communication and dissemination of what we find out, we run distance learning courses. So we run some short courses, which are more for the general public, and people with a general interest in science. But we also do a master's program by distance learning. So that's quite good. That's enabled a lot of people who've done degrees in other science areas to get a detailed knowledge of astrophysics, which has then enabled them, for example, to go on and do their own PhD research, which is really good. And another part of what our outreach group, which is led by Andy and features Stacey and Jenny and Emma and all the other people you'll be talking to today, is public outreach activities, so links with schools activities, and basically getting the widest possible group of people knowing what we're doing here in Liverpool and excited about the universe. Right, so I think I've probably spent longer than I should have done anyway. I always waffle too much, I just get carried away on these things. But again, it's great to have you all here working with us this week, and I'll hand back to Andy, who I think is going to say some more about the Liverpool telescope.
Yeah, thanks, Phil. Excellent. Yes, so as Phil has said, there's a lot of different research going on in the department, but quite a lot of that involves this thing, which is our big toy, called the Liverpool telescope, though it's not in Liverpool for obvious reasons, mainly the weather, but there's lots of other ones as well. We actually have it on the Spanish island La Palma, one of the Canary Islands. Just out of curiosity, can you give me a green tick if any of you've ever been to a Canary Islands, just out of curiosity? There's a few appearing there. Excellent. Oh, and a few no's. Has anybody ever been to La Palma? Because it's not one of the more touristy ones. Anybody been to La Palma? Yep, Stacey and Jenny have. Oh, I have. There we go. It's not the most touristy one because it doesn't have beaches, but it has an amazing extinct eroded volcano, and you can see that at the top of the picture on the right here, that kind of giant crater is an extinct eroded volcano. And the picture behind me is taken standing on the lip of that crater. And it's one of the best places in the world to put a telescope. It's absolutely stunning. Incredibly dark nights, very good weather. The cloud tends to be below you because it goes round the mountain rather than over the top of it. So it's a beautiful place. There's actually an active volcano in the south of the island, but the top of the island, the north of the island, is very much extinct. The observatory is called the Roques de los Muchachos, the Observatory of the Friendly Rocks. And there's, I think, currently 14, possibly more telescopes coming soon up there, including the largest optical telescope in the world. And it's an international project from a number of countries around Europe. And so it's an absolutely stunning place to put a telescope. We're very lucky to be able to have the LT there. And although it's not the largest of the telescopes up there, it is a little bit unique. Can I have the next slide, please? I feel as I'm doing a briefing. Other way, Jenny, sorry. Brilliant. Okay, so a few stats. We need some stats. So it's fully robotic, which I'll explain in a minute, but it has a 2-meter mirror. So the main part of any telescope is the primary mirror or lens. Nowadays, they're nearly all mirrors because you can only make lenses a certain size before you can't see through them anymore. So we have a giant concave mirror at the bottom of the telescope, which is 2 meters across. The whole telescope itself is nearly 9 meters high, weighs about 24 tons, and it sits in an unusual dome. Most people think of domes as sort of hemispheres with a slot in them. This one opens all the way, leaves the telescope sitting out in the open air, as you can see in the picture at the bottom. That means it can react more quickly. And that's an important thing for this telescope. It's designed to react very fast to things that are changing out in the universe. So it moves very quickly. Most telescopes aren't actually designed to move very quickly because the amount of time you spend moving isn't important. But this has to react quickly. And if it can get somewhere in a minute or less, that makes a big difference to the kind of things it can see. And as well as being quite a big, very rapid telescope, it has different instruments on the back. So a telescope collects light and brings it to a focus. If you then want to do something with that light, you've got to put it in some sort of instrument. So we've got cameras. There's an infrared camera and an optical camera, for example. But you also might want to do something like use a spectrograph. A spectrograph takes the light and essentially splits it out into the rainbow so that you can accurately measure the precise amounts of each wavelength of light. There's a thing called a polarimeter, which looks orientation of light, tells you something about magnetic fields. So there's all these different instruments on the telescope as well, and you can choose which one you use to take the observations to do the science that you want to do. And so a lot of people get to use this telescope. 90% of the time it's doing research, so it's working for professional astronomers, and it might take observations for 10, 20, maybe even 30 different astronomers every night, all of them doing different studies of how the universe is changing. But 10% of the time, a tenth of the time, it's actually doing observations for people like you, people in schools, right the way from primary right through to A-levels and higher and so on. And those two work side by side. The telescope doesn't care whether it's observing for somebody doing research on a distant galaxy or somebody studying the classification of galaxies in school. It will do its observations at the best possible time. I'll be talking a little bit more about that later, but grab any of the NSO team at any point during this week if you want to know more about that. If you've never used a telescope for yourself, then now is your chance. It's completely free for any school, so you're welcome to get involved. The next slide, please. Lovely. So what kind of things does it look at? Well, it's essentially looking at anything where change matters. That might be an intrinsic change, something actually physically changing, or it might be a change due to movement in a system, which allows you to see what's going on. And you can see from this list of headlines here, there's quite a range. An important one is extrasolar planets. These are planets going around stars other than the sun. And you can see here an illustration of one of the systems that we were able to get involved in, the TRAPPIST-1 system. And you see a lovely picture there of seven rather nice planets, which is completely fake. We have no idea what they actually look like, but we do know what temperature they are and how big they are, because they're not discovered by getting pictures of them. They're too far away, they're too small. We discover them because as they orbit around their star, they occasionally pass between us and the star, and that blocks out some of the light. It's called a transit. And while it's blocking out some of the light from the star, if you're very carefully looking at that star, you'll see that star gets very slightly fainter. And then once the planet is orbited on, and you're seeing the whole star again, it goes back to its normal brightness. So if you look at stars night after night after night and keep measuring their brightness time after time after time, you sometimes see these little changes in brightness. And that's how we find quite a lot of planets, both from the ground and using telescopes in space. There's a very famous one called Kepler, which has found lots of these things. And we are getting very good at finding these planets, but TRAPPIST is unusual. Finding this many planets going around the star is unusual. But what's particularly special is they're all quite similar to the Earth. There aren't any giant ones like Jupiter or Saturn or anything like that. These are all smallish planets which are likely to be rocky rather than gas. And so this is 7 places where in principle we might have a chance of finding something a little bit like life. And indeed several of them are the right distance from the star that the surface temperature is somewhere between 0 and 100 degrees centigrade, basically. So they could be liquid water, which we think is probably very useful for getting life going. So finding these planets, studying them is an important part of the work that the telescope does. Go to the next slide as well, please. Thanks, Jenny. Slightly more dramatic and a personal favorite of mine is something we look at is things like this. This is a thing called the Crab Nebula, sometimes called Messier 1. And this is what's left of a star that exploded. We saw it explode about 1,500 years ago. No, this one about 1,000 years ago. And it was a big star. It reached the end of its life and it just went kabloom. They are enormous explosions. They let out more energy in a few minutes than the star will do in a billion years. Sorry, the sun will do in a billion years. So they're incredibly dramatic explosions and they're tearing apart the outsides of stars. And so we can learn a lot about what stars are made of by studying these things. But more importantly, those explosions take the elements that were surrounding these stars and they start smashing them together really hard. And that can actually make them stick. That can make new elements. And elements heavier than iron won't form inside stars. They can only form during these explosions or similar things. And so by studying supernovae, not just old ones like this, but supernovae as they're actually happening, watching the explosions, lets us see where a lot of the elements in the universe came from. Most of the different elements in your body have been inside these exploding stars. You wouldn't exist without them, but there's still some important questions we haven't understood. So studying things like supernovae, gamma ray bursts, which is kind of supernovae with attitude, they're even bigger. These really help us understand what's going on. Can you have the next one, please? Lovely. And then we've got active galaxies. This is another artist impression, I think. Yes, this is an artist's impression rather than an observation, but we've got almost as good with actual telescopes. Most galaxies, like the Milky Way, sit there with stars in them. And basically, most of the light we see comes from stars or pockets of glowing gas. But some, the center of the galaxy is incredibly bright, often brighter than the rest of the galaxy added together, brighter than hundreds of millions or hundreds of billions of stars. And what's happening there is right in the center of the galaxy, there's a very massive black hole, typically a few million times the mass of the sun, all squeezed into one black hole. And in most galaxies, they have these black holes, but they're sitting there doing nothing. In some galaxies, there's stuff falling in. Now, anything that falls into a black hole disappears and is gone forever. But while it's falling in, it can start moving very fast. And before it disappears into the black hole, you've got material moving very quickly, smashing into other stuff, bits of stars smashing into bits of other stars at close to the speed of light. And it produces vast amounts of energy. And when we see that in the center of a galaxy, that's an active galaxy. And they can produce very dramatic things called jets. You can see in this picture here where material doesn't quite fall into the black hole, but gets squirted out along the axis where it's spinning and things like that. So they're very dramatic. And again, they tell us a lot about extreme physics. We can't get stuff and throw it into a black hole on the Earth. That's not sensible or even physically practical. But we can see it happening halfway across the universe, and we can study it and we can learn about things. So that and asteroids and all these other things in the universe that are changing are important parts of what the telescope is doing. But alongside that, there is the work we do with people like yourselves, with schools. Go to the next slide, please, Jenny. Lovely. And that is the National Schools Observatory. You will learn more about this during the week, so I'm not going to go into huge amounts of details. But if you haven't come across it before or haven't looked at it, much, then have a look at the website at some point this evening or tomorrow or something like that, schoolsobservatory.org. We've been around for quite a long time. It was set up in about 2004, and the core of it is allowing you and anybody else in the school in the UK or Ireland to get your own observations through the Liverpool telescope. Essentially, it's a system to guide you towards doing that. Using a big telescope like this is not necessarily simple. There's lots of decisions that you have to make. Some of those decisions are interesting, which object you want to observe, when, that kind of thing. Some of them are really boring. How do you calculate the exposure time for the particular filter you're using? You do not want to go there. So we will do that work for you on the website. But alongside that, there's a lot of other material, bits of information about astronomy. You might find it a useful resource to start with when you're doing your research for your projects, for example. There's news, there's different kind of learning activities, there's stuff for clubs, there's stuff for teachers. So have a look, but also talk to your teachers. If they don't know about the Schools Observatory or they haven't told you about it, get them to have a look at it. Get them to sign up free and play with it for themselves. They will thank you. It's an extraordinary thing.
So yeah, it's good to start thinking about what the next steps are that you need to take if you really are considering that career in astronomy or physics with astrophysics or astrophysics. So let's see. Here we go. Okay, so first of all, we want to think about sort of what is astrophysics. I mean, you're all here, so you've already got some ideas of what astrophysics is, but in terms of what it actually entails, if you want to pop some things in the chat about what you might think astrophysics, especially after the experiences that you've had today, you know, what do you actually think astrophysics entails? What do you think it means to be an astrophysicist? Yeah, lots of data analysis. Exactly. Especially you'll have experience of that now from the last few days. Anyone else got some ideas about what you think it might entail to actually be an astrophysicist? Yeah, small moments of discovery. Brilliant. Ali, if only face-to-face, perhaps. Yeah, using data to draw conclusions, coding data, yeah. Understanding our universe for sure, yeah. Understanding those big questions, studying the observable universe. Yeah, great. So yeah, so you've got some yeah, and that's an excellent point. Sharing discoveries with others, we'll touch on that in a moment as well. Certainly about those communication skills, how we share these things that we found out with other people from all different walks of life, either other scientists or the general public, or school pupils, or pupils like people like yourself, at, you know, at A-level sort of level. Great, yeah. So some really good suggestions there. So if we look into the sort of terms of a definition, in terms of the official definition, it certainly says and certainly summarizes that astrophysics is sort of how we apply the laws and theories of physics and into interpreting astronomical observations. So that's the official definition. But as you've already started to break that down already in some of the suggestions and some of the comments that you've made. So another thing to bear in mind as well, actually, is it sort of touches on it here in this definition. Sort of historically, astronomy and astrophysics were often deemed as quite separate disciplines, where astronomy was sort of focusing on that observable aspect, but astrophysics sort of and focusing on the application of physics to those observations. However, these fields are very much merging at the moment, you know, merging now, because you'll do certain aspects of all of that as you go through into any sort of astrophysics or astronomy career. So they're not really that separate anymore. And as you've all alluded to with some of those comments, it's essentially a massive wide range of skills that you will learn as you study astrophysics and go into doing astronomy with physics, or whichever sort of specific course you study or path you take. So you're going to do a lot of physics, there's going to be a lot of computing, you've mentioned coding and things, a lot of data analysis, doing some advanced maths, so the astronomy side of things, so the observable side. There'll be some chemistry brought into that as well, and especially that communication side as well. There's a really long history of excellent science communication in astrophysics, physics with astronomy, because these are such big concepts and such big ideas that are often intangible because of the way in which we observe them. So being able to communicate these things clearly is a real skill set that comes with being an astrophysicist as well, that you can learn and grow during your career. So those combination of skills can really equip you with a really highly transferable skill set. And that means that even if you sort of come to astrophysics with an idea to be an astrophysicist or an astronomer, whichever path, then because of the transferable skill set that you gain, there are so many different avenues that you can explore with that as well. So it can open a lot of interesting doors to a lot of interesting careers as well. I mean, from my own experience, I didn't study astronomy or astrophysics, but I studied deep sea environmental sciences. And similarly, I developed a whole suite of excellent skills. So then I've been able to come and work in astrophysics and have a really rich career and a really rich experience. So it's about this really excellent, highly transferable skill set and studying something that you're interested in, which helps you develop that really well. So as we've sort of touched on, the way that astrophysics and astronomy often interlink now, when you're starting to think about looking at universities and starting to do your research in terms of which university you want to go to, it is worth bearing in mind what is in the name of the course that you are going to apply for and that you're researching. So you might find that it's called astrophysics, you might find that it's called physics with astronomy, it could be physics with theoretical astrophysics, with cosmology, with nuclear astrophysics. The main thing really is to, when you're doing your research, is to go and look at each course pro forma, have a little look through different module options. Each university will have a dedicated page and it will break things down. We're going to look at the offering from our course a little bit later, so you'll see, and Andy will sort of explain a lot more about how all those different modules and things work. But this really does form part of your research, really, to make sure that you're going to the right place and that you're taking the right route through your course. You might also see a few different iterations of the way the course is laid out. So it could have a foundation year, it could be described as a BSc, which is a Bachelor of Science with honours, and it could be described as an MPhys or an MSci. With the foundation year, that means that you would do a 4-year programme where you would come in before and do a year before starting the actual degree itself. And they can be really useful sometimes in case something's just, with the best will in the world, you didn't have a good day on an exam, you know, and you just didn't quite hit those UCAS points. So some universities do offer that foundation year. And I've done a lot of research in a previous role that actually shows students who come and do a foundation year still do really well on their actual degree course as well. So they can be a really positive thing to do if you need to do that foundation year. It's not a problem at all. If you might just go straight through into the BSc with an honours, and the honours project, the honours part just means that you're going to do a research project as part of your degree programme. And then when it's got the M in front of it, that can mean that, again, it's a 4-year programme, but you start at the bachelor year and you do a 4-year programme, and that's got an integrated master's to it as well. So there's a few different options that you can explore when you're starting to do your research. One really useful resource is this link that I've put here at the bottom for the IOP My Physics course. We can quickly take a look at that. Let's see if I've got the technological know-how to switch to the web page. Let's see. Can everybody see that web page okay? Brilliant, thanks for popping that in, Jenny. So unless I hear otherwise, I'll hope that everyone can see this web page and that the change of share has worked.
It's fine, yeah.
Brilliant, thanks, Andy. I couldn't see any nodding faces because it's all on my screen. So this is a really good research resource for you to use, mainly because you can sort of filter between different subject combinations. So you'll see here, you can also filter through locations. At the moment, I've got it set to the whole of the UK. I'm going to do a drop down here for subject combination. So I'm going to choose physics, astrophysics, astronomy, space, cosmology. So it's got all of those different iterations there, which is really handy, you know, in case you forget which search term to put in if you're searching manually. You can filter by university as well, if you wanted to. So, you know, all the universities across the UK that offer any of these combinations of courses. You can filter by location. So, you know, if you really want to know that you want to stay in England, or you think, oh, I'll go to Scotland or Wales, or if you want to go to or stay in Northern Ireland, you can filter there. One of the most important things, and I think really valuable things that this IOP, the Institute of Physics website, offers, is that you can filter by the status of degree as to whether it's accredited or not. So I would always suggest looking at the accredited courses. What the accreditation means is that the IOP has worked with that university as an independent sort of independent evaluation regulator, to make sure that this degree has hit, the degree that you're looking at has hit a certain set of standards, that are that really just make sure that that is a really, really solid degree, and that the content and the standard of the degree is sort of informed by the wider physics community, and that everything is really up to that standard. So that's a really important and valuable part of having a look through this website. And you can also look at course duration as well, so whether it's 1 year, 2 year, 3 year or longer. So yeah, so I would really recommend you go away and have a look at that in your own time, and as and when you're starting to make those, or trying to narrow down your decisions about which universities you want to go to and start exploring. So let's go back to here. Okay. So yeah, lots of different iterations of the type of degree that you might want to study. And again, it's, you really just do your research, go onto the university web pages, have a look at the different pro formas on there. In terms of grade requirements, these will vary from university to university. So for instance, the University of Manchester, that's sort of got the bar sort of about as high as it goes in terms of UCAS points. So it's 160 UCAS points, so you're going to need an A star, A star, A to get into the University of Manchester, compared to the University of Hull, which is 3 Bs, so 120 UCAS points. But generally, you do need that A, B, B or above if you want to sort of have a wide range of options available to you, and must include maths and physics as well. Something that you can do as well on the IOP website, which is another really useful thing to do, is you can filter by, where's it gone? You can filter by UCAS points. So you can use the scroll bar, you know, when you've got an idea of sort of what range you're going to be looking at, and that will change those options that come in below as well. So that's another really useful thing that you can use. So yeah, again, that's a really, really useful resource. And when you do start to narrow down that sort of list of universities that you might want to look at and start sort of comparing what the exact offering is, there's going to be a lot of choice out there. Try not to be too overwhelmed with it. You can make yourself a checklist to be like, okay, let's narrow it down this way. And when you're thinking about which university you want to go to, you do want to look for that unique selling point. What does that university or those universities offer that really sparks your interest, that thinks, oh yeah, okay, that's something that's got an element to it that I really want to study, or that's in a location that I think I'm going to really fit in with, and things like that. You'll see on this map here, this is just an indication of sort of the different locations that you could go to if you wanted to, when you want to study one of these degrees. So there is a huge range of choice there. One of the most important things is to attend open days. Make sure you ask questions when you do go to those open days, and remember that anybody that is at an open day is there to answer questions for you. So you know, the only silly question that is one that goes unasked. So every single question that you can ask is really valuable and really important, and those people are there to help you make the right decision as and when you do start to attend those. Ignore sort of fancy Nobel Prize winners and fancy titles like that. There are going to be some universities that, you know, really have some high flyers there, and that's great, and that's wonderful. But the most important thing when you're looking at universities and when you're going to these open days and having talks from the different departments is to imagine yourself being taught by those people. Listen to what they're saying, listen to the way that they're communicating. Again, it's those communication skills, and whoever you're inspired by, whoever you think, okay, I'm going to learn from these people, they're going to inspire me, they're going to help to get the best out of me. that's what's really important when you're making those choices to go to university. And again, it comes back to location a little bit as well. You're going to live somewhere for at least 3 years, maybe 4 years. You might even stay in that place after you graduate. A lot of people move to a new city and they stay there for years afterwards because they make a whole new life and friends. But then equally, you might have a really nice situation going on at home and you're really comfortable there, and that's going to provide you with the support that you need to study well. So then you can stay there as well, you know, and so really do think about where you want to be and choose the right thing for you. You can move into student accommodation and make lots of new friends, or you could stay at home and be comfortable. And the main thing is that, yeah, you just choose the best thing for you. And also whether it's going to be a campus versus a city university. So the universities in Liverpool, certainly John Moores and the University of Liverpool, we are sort of integrated into the city. So we are very much city universities. When you're a student in Liverpool, you are integrated into the city, you're a citizen of the city essentially. Some of the universities have it slightly different, where their campus is sort of just outside of a city and it's very much like a university village. And that suits some people better as well. So these are things to think about when you're making those decisions. And most importantly, again, are you going to be happy there? Because if you're happy, you're going to study well, you're going to get the most out of the whole experience. So this is where I will hand over to Andy, because now we're going to have more of a sort of detailed look about what it's like to study astrophysics in Liverpool specifically. And Andy is the best person to be able to bring those to life.
Yeah, thanks, Emma. I'm not really going to, I mean, what I want to really talk about is Liverpool as an example of the sort of astronomy and physics degrees, because it shows you how it can be different from somewhere else, and that's the kind of thing you might look for, whether you like it or don't like it. We offer 2 basic degree programs: the physics with astronomy, which is the bachelor's degree, and then the astrophysics, which is the master's. The only reason they're called physics with astronomy and astrophysics is so that we don't have to remember to say that's the master's and that's the bachelor's whenever we talk about them. So they're essentially, at least for the first 3 years, the same degree. It's just if you go on to the 4th year for the MPhys, you end up with the master's. We do them jointly with the University of Liverpool. This is pretty unusual, actually. I think it's still unique. Going back a decade and a half or so, we had this rather weird situation that there were 2 universities in Liverpool, one of them with a big astrophysics research institute, who were doing lots of astrophysics, but couldn't teach a full physics degree because we didn't have the other people doing the other parts of physics. And you had this physics department at Liverpool University with no astronomers, so they couldn't do an astrophysics degree either. So we just got together. And for the last, I think it's 18 years now, maybe even 20, we've been teaching these degrees together. So you would be joining the cohort of physics students at Liverpool, and we teach the astrophysics parts of those degrees. It works very well. You sort of end up with the benefits of both universities, but all of the coherence of 2 departments. It also means there's a lot of staff. If you add the 2 departments together, I think it comes out as nearly, can't remember the most recent number, I think it's something like 80 staff in total. And we take about 120 students a year, so the staff-student ratio is pretty good. Doesn't always show up in the league tables because they sometimes count one university rather than the other, but ignore league tables, they're gibberish. I tell you that as a statistician. So just as you see here, there are typical entry requirements, ABB, AAB. They are different for the BSc and the MPhys. But once you've joined, you can do any of those degrees, depending on the choices you make as you go through. So we have students, for example, who start doing a BSc in medical physics and then end up doing a master's in astrophysics. So to a certain extent, it doesn't actually matter what you apply for. You should probably apply for the one you think you want to do. But if you're unsure, go for the bachelor's, go for the BSc, the entry requirements are a bit easier. This isn't true for all universities. We've deliberately designed the degree program so that it's very easy to switch between things. Essentially, you make your main decision about which physics degree you want to do at the end of the first year. So you've got that entire first year to make those decisions. There's various things which come in to being, you know, a degree in a large physics and astronomy department. So it is accredited by the Institute of Physics. It's really important. There are study abroad opportunities that the universities, particularly Liverpool University, offer. So, for example, there's currently a scheme where you can spend a year learning in China if you want to. Whether that continues or not is anybody's guess. These things tend to be negotiated year by year, but there are these opportunities coming along. But for astrophysics specifically, we have two things which we consider to be quite important. If you're going to do an astronomy or astrophysics degree, you'll have realized already that data is an important part of that. There's underlying physics, which you have to know and you have to study, but there's also learning how to deal with astronomical data. And for that, we have two things which are important. First of all, the Liverpool telescope, which has been mentioned several times because we like it and we're proud of it and it's our big toy. We use that data for that in final year projects. So for example, I run a project pretty much every year where we just give time on the telescope to a student and I work with them to decide what they want to do with it. And some end up studying asteroids or variable stars or active galaxies. Lots of different things happen with that, so that's quite fun. And also we think it's important to get some actual experience of working with a dark night sky, which is tricky in the UK. Even if you can find somewhere dark, it's usually dark because it's cloudy. So going somewhere that's a little better than that is important. So every year that there isn't a pandemic, at the end of the second year, we take all the students out to Tenerife, which is the island next to the one that has the Hubble telescope on, another very good observatory. And everybody spends a week out there using several telescopes, getting your own data, really exploring the night sky. We also drag everybody out for at least half an hour to an hour to just sit or lie down on the ground and look at the sky because it's absolutely stunning. Even without the moon up, the skies are clear enough that you can see where you're going by starlight. It's an absolutely beautiful place. And if you've never seen, the Milky Way spread out above you, not sort of squinting and trying to see, is that the Milky Way or not, but actually walking outside and saying, oh, that's the Milky Way. Until you've seen that, you really don't understand what the sky can do to you. I was a physicist until I went observing, and then I became an astronomer. It just changed the way I looked at things. It's beautiful. Can I have the next slide, Emma? So going into a little bit more detail about the specific degree, these are some of the modules that are covered in the first couple of years of the degree. Some of them are optional, some of them are core, but it doesn't really matter too much of this. You will notice that a lot of them are basically physics. That's because this is, as with any decent accredited degree, it's a physics degree where you specialize in the universe. That's what astrophysics and astronomy really are. So you have to get this core physics in order to be able to appreciate the universe, in order to be able to understand and explore the universe properly. And that's covered in all of these different areas: quantum mechanics, dynamics and relativity, and so on. You'll have come across these terms if you're studying physics at the moment. Maybe you've come across them in different contexts, but they're essentially the same things. One important thing about this is, alongside the actual physics, there are the skills you need to take it further. So there's the computational side, the labs, which is the practical physics, the statistics, which seem a little dry when you look at them there. But the course, as with any decent course, is very carefully designed so that, for example, when you're studying wave phenomena, you'll be doing labs on wave phenomena, so that you get the practicals to reinforce what you're learning in the lectures and the tutorials and so on. And that works very well. We find that students pick things up a lot more quickly. The more traditional degree, the kind of thing I did, they'd be completely separate and there wouldn't be any connection between the two. And frankly, it was a nightmare, really hard to learn anything. So this works an awful lot better. So this is the core physics. You'll see the computational thing there. That is because if you want to be able to do research, you can't rely on software other people have written, because they won't have written the right software because you're the first person to do this. And so every physicist, every astronomer can code. And this causes panic in large numbers of people because they think, I can't code. And you can, because you're clever and computers are thick. Always bear that in mind. Computers do exactly what they're told to do. You just have to learn how to tell them to do it clearly in words of one syllable. It's like having a really stupid little brother. That's the way I look at it. I know this because I was the really stupid little brother. I got two older brothers. So you will learn how to do coding, and you will learn it fairly easily. And you will get to the stage where you never have to use Excel ever again. which is, to me, I hate Excel. It just drives me berserk. But I can do things using code faster than I can do them in Excel and with larger data sets. And to me, that's just made my life so much better. So you may not specialize in the computational side as I did, but you will learn how to code. You will learn how to use computers to do what you want rather than what they think you want. Research software doesn't have paper clips popping up and telling you, do you want to write a letter? It doesn't work like that. It actually does what you need it to. Can I have the next slide? So alongside the core physics, there's the astronomy and the astrophysics, and there are some core astronomy modules that you would be studying if you were doing an astrophysics degree. The practical astrophysics is the observing, and that includes the field trip, but it also includes lab work, experimental work, data analysis, the kind of things you've been doing, but slightly more advanced. Stellar physics, how stars form, how they evolve, what happens inside them, how the elements are created. Observational astrophysics again ties into the use of telescopes, but also other techniques, how to use a radio telescope, why do we need X-ray telescopes, that kind of thing. And then following on from the stars, you need to understand the galaxies. How do they form? Why do you get particular kinds of stars in particular areas of galaxies? How do galaxies evolve? And then tying that together into the entire universe, you have relativity and cosmology, which is essentially the complete history of the universe up to now and what's likely to happen in the next 100 billion years. So it's a big subject. And so they're the core things that you will need to know if you're going to come out at the end of an astronomy degree and have a concept of how everything fits into the universe. And then you get to choose optional modules. You can do a little bit more about planetary physics. You might look more at the atmospheres of stars, and so on. And you can also choose some of the physics optional modules. So there's a nice way, there's a nice variety, picking and choosing the areas that interest you. Because by the end of the first year, you'll have a much better idea of what does actually interest you. You might have come in thinking, I want to be an observational astronomer, and then actually think, oh, this theoretical stuff's really cool. And you can adjust and adapt as you go along. I'm one of the ones who changed. My first degree was actually purely computational physics. And then I finished that and thought, well, that was all right, but I want to do something a bit different now. And I looked around and discovered that you could do astronomy, which hadn't even occurred to me up to then. So I changed from computational physics to astrophysics, did a PhD in astrophysics at the Glasgow University, loved it, and I've stayed there ever since. But if I'd done that and thought, well, that was all right, but I want to do something different, I could have done, because the skills keep moving on and keep changing, and keep being appropriate to wider things, which is great. The other thing to bear in mind is I've given you an outline of one degree, the degree here in Liverpool. Other degrees will have similar things, but they will also have differences. But the biggest differences will not be the degree. There'll be differences in the sort of research a particular department does, which will affect things like the final year projects you do. But the core physics, the core astrophysics won't vary too much between universities. If it does, they wouldn't be able to get accredited. So that core physics is basically the same. The most important thing, I think, and this is not everybody agrees with me, but I think the most important thing is, will you like being there? Will you enjoy it? I've either studied or worked in some quite different universities. My first degree was at Warwick, which is a very campus university. You hardly set foot off the campus for your entire first year, except maybe to go shopping. That's it. Then I went up to Glasgow, which is very much a city-based university. I had a job in Southampton, which is kind of halfway between the two. Liverpool's got a campus, but it's a campus that's part of the city and so on. They've all got different feelings. And you need to visit somewhere to really get a feel for it, even if it's only for half a day for an open day. I originally came to Liverpool for 2 years. I was on a 2-year contract, and I didn't really expect to enjoy it. I thought the job was nice, but I didn't expect to like Liverpool. And I've now been here 22 years because I really do. And it's partly because I like the city, but it's also because I don't live in the city. I'll show you. If you look at my background now, this is the beach 100 meters away from where I live on the Wirral. So I live here, but I can work in Liverpool, and I just get the train backwards and forwards. And that really suits me. Other people, that would drive them insane. I've got one friend who spent so many years living above a nightclub that he can't sleep unless there's incredibly loud music playing. So he has to live somewhere where he can play incredibly loud music without annoying the neighbors. And so everybody has different things that suit them. This suits me really well. So whatever you're thinking of doing, visit and explore, chat to people who are there, chat to students if you can manage it. If you go to an open day at university and they won't let you talk to students, there's probably a good reason. But most universities will want you to chat to the current students, because then you will get an idea of what it's really like. The most important thing for any lecturer in a university is not to get as many students as possible. It's to get students who want to be there, because they're better to teach. And you'll learn more and everybody will have a better time. So when you go to open days, ask the questions, chat to people, because everybody wants you to make the right choice.
Sort of what's left to find out, what are the unanswered questions, and how do we go about trying to answer them. So initially, kind of an idea of like, you know, what is astrophysics? So obviously you'll have all heard of astronomy. A lot of you might be thinking about studying astrophysics at university. As Phil said before, it's a branch of physics. So it's doing science, it's studying stars, everything else that's in space, but applying the laws and theories of physics that we know about to objects that are in space. And a lot of that is down to interpreting observations, because the thing about astrophysics that's different from most of the sciences is that we can't in any way, shape or form control an experiment. So actually often we call it an observational science rather than an experimental one. But when I was thinking about it more and more, actually astrophysics today involves so much more than just observing through telescopes and interpreting data. There are experimental branches of astrophysics, certainly when you're thinking about the production of elements in the early universe, or when we're looking at, you know, nuclear fusion and how we can try and harness nuclear fusion here on Earth. There are certainly branches of astrophysics that are experimental. There's obviously a lot of maths involved as well. Full disclosure here, I'm not a huge maths buff. I really struggled with maths at school. But when I started doing it at university, especially as part of astrophysics, because I saw there was a point to the maths that you were doing because you were using it as a tool to explain things, I found it much easier to get on board with. So there's obviously a mathematical side to astrophysics. There is the observational aspect. You know, this is a telescope. It's not like the other telescopes we've seen, because this one is actually analysing radio waves, not visible waves of light like we might be used to. And the reason that this one's quite interesting is because it's here, it's in the UK, it's Jodrell Bank, which is in Cheshire, and it's one of the biggest radio telescopes in the world, and it's actually going to be the headquarters for a brand new international radio telescope project called the Square Kilometre Array, which the telescopes of which are all are going to be based in Australia and South Africa, but all the data is coming back to Jodrell Bank in the UK, and it's going to be processing, you know, hundreds of terabytes worth of data probably every few minutes. So it's a huge area of advancement in science, the observational side of things, but also the data processing and the technology that comes around with that. And as Phil mentioned in his little introduction to the department as well, supercomputers, simulations and using supercomputers is a huge aspect of astronomy now, especially when we're looking at things like things that we can't physically see. So trying to recreate the conditions of the early universe and how galaxies are expanding, where dark matter lives in the universe, but also things like, you know, my personal area of astronomy is looking at supernova explosions. And actually modelling how does a star explode, we've only been able to actually physically understand how that process happens in the last few years. Before that, we didn't even know what could trigger the star to explode. We ran simulations and we had to put a kick in there artificially to make the stars explode. Now, obviously, that means you're not understanding all of the physics, because if you're having to input something like that, it tells you you've got a gap in knowledge. So these kind of supercomputer simulations where you can get more and more information, more and more particles within the simulations, tells a huge amount. So I started off thinking, well, you know, astrophysics is an observational astronomy, is observational science. Actually, it's much more than that, and it combines all these different areas. And it's all about this idea we talked about this morning, asking questions. There's never a stupid question. There's never ever a stupid question. It's a huge part of the scientific method and learning, is that we constantly ask questions. And this is sort of the old school idea, is that, you know, you make some sort of observation and that leads to you having a question, and then you'll research that area, you'll propose a hypothesis, test with an experiment, analyze the data, have conclusions, and that might lead to more questions actually. So it's this big process. Now, where astronomy is different is we can't test with experiment. We can't do that. We can't tell the universe to do something for us in a particular way. So this is a bit more like what the scientific process is like. You're still making the observations, thinking of the questions related to that and proposing hypotheses, but it's much more about developing predictions that you can physically test, and that might come from a computer simulation, it might come through you know, a mathematical concept, and then gathering data. And what we can do in astronomy is still gather data, even though we don't have control over how that data is produced. We don't have control over when a star explodes or how a galaxy decides to rotate. We can still gather that data and then use that to develop theories. So there's a big statistical element in astronomy, because we've got to try and understand how things work by just taking lots and lots of examples of them. If we just look at one object, you can't draw big conclusions from that. So building up big statistical samples is a huge part of astronomy now, which is why actually big data and having huge amounts of data to process is becoming more and more important in astronomy. So if we're going through this process, and we might think about what questions are there still to answer, you know, astronomy is an ancient, and I mean an ancient science, you know, people were doing this in Persia, in Asia, in China especially, you know, thousands and thousands and thousands of years ago. You know, the Mayans used aspects of astronomy. So if it's been around for so long and we've been thinking about these questions for so long, what on earth could there still be to answer? And that's what I love about astronomy, and that's why I'm still in astronomy. You know, I'm going to prove my age now, but I started my degree in 2004 and just never left the field, because I just loved that I was constantly being able to learn new things every day and question new things every day, and that there was always something still to find out. It's a very active field of science. And that can be something as basic as looking at our moon. Our moon, our nearest neighbour in space, we see the same side of the moon every time. The moon is tidally locked with Earth. We always see the same face. And yet, in October, I'll see if this works with the laser pointer. In October of last year, just last year, this huge crater at the bottom of the moon here, which, as I said, we've been able to observe for thousands of years, even with telescopes for thousands of years, well, hundreds and hundreds of years. We discovered water in this crater using a telescope mounted to an aeroplane called Sophia. It's a NASA aeroplane. I've got a soft spot for it now because one of our ex-PhD students, Maisie, is currently in the US working on this telescope on this aeroplane. And they discovered water just here on the side of the moon that we've been observing for hundreds of years. So there's always new things to discover. And the differences that we can see that help us to understand how the universe formed, how the solar system formed, this is the far side of the moon. So this is the other side of the moon that we just don't see. And you can see the difference between the side that we observe and the side that we can never see. And to think that the first person to ever see this was Michael Collins in 1969, the person that was left on the aircraft, on the space shuttle that went around the moon while the other two landed on the surface. He was the first person to ever physically see this. And it looks entirely different. You can see it's potted with a lot more craters. It gets hit by a lot more meteorites. And if you have any questions about meteorites and space rocks, Jenny is our expert. She's a planetary scientist. So any questions towards that sort of thing, please feel free to ask her during the week. But this one thing that's interesting about this is that it tells of a few things. Obviously, the moon doesn't have an atmosphere and the Earth does. The moon is tidally locked with the Earth. So actually, the side that's facing the Earth gets saved from a lot of these meteorite impacts because we are in the way. So the Earth gets hit by these objects as well, but we can't see it the same as we can on the moon because we do have an atmosphere, we have weather, we have erosion. So being able to study something like the moon that doesn't have the geological processes that go on the Earth helps us to try and understand some of the formation of the early solar system as well. So even looking at our nearest neighbour in space, there's a huge number of questions that we still don't know the answers to. We still don't for sure know how the Earth and the Moon formed. We think that we were that in the early solar system, what was the Earth was hit by an object which could possibly have even been the size of Mars, and that split it into two and made what we now know as the Earth and the Moon. But we don't know for sure. We didn't think that water could survive on, you know, the surface of the Moon that was actually facing the sun, that didn't constantly live in shadow. We found water on the Moon before, but it was in areas of constant shadow on the surface. So this is a new discovery. So even our understanding of where water could exist has changed just by looking at the Moon in the last few years. You know, aside from the Moon, we've got the sun. The sun is obviously our closest star, the one that we can observe in the most detail, but we still don't understand everything about it. There's some weird quirks to the sun in that the surface temperature of the sun is only around 7,000 Kelvin, about 6,800 Kelvin. But if you go down just slightly into the sun's surface, the temperature is millions of Kelvin. How can you get such a temperature gradient in such a small amount of space? We still don't fully understand that. It's obviously the place that we look to try and understand nuclear fusion, a process that we want to harness here on Earth to try and help us with our energy needs. It's got weather. We have space weather. You can see my background is the aurora, which some of you might have been lucky enough to see. This is charged particles coming from the sun, hitting the Earth's atmosphere and traveling along the magnetic field lines to the poles of the Earth. And we get these huge solar flares. We know that the sun has a cycle it goes through where it's very active and very quiet. But actually at the moment it's quite quiet when we're expecting it to be more active. So what's causing that? We don't understand so many things about even just looking at our closest star. Magnetic fields are an enormous thing in astronomy, and we sometimes joke, especially with our PhD students, that if they ever go to conferences and listen to talks and people explain things with the concept of a magnetic field, it's because they don't understand what's going on, because magnetic fields are so complicated and we know so little about how they work in practice with an object like this that is differentially rotating. You know, the whole surface of the sun is not moving at the same speed. You get convection patterns obviously bringing the heat to the surface of the sun. There's so much going on there, so much movement, so much dynamism, things moving, that the magnetic field lines get twisted, they break and snap, which is when we get a big flare coming off the surface with a bunch of material in it. Just trying to understand these magnetic field lines, where these particles travel, you can see how complicated the magnetic fields are just by looking at this much detail on the surface. And then, yeah, when you get these kind of magnetic field lines break because they get twisted so much, they snap and propel all this material around the universe. And obviously trying to predict space weather is quite a big thing, because we need it to try and protect ourselves. If we get huge bursts of solar particles hitting the Earth, it can do damage to satellites, and we rely on satellites so much for our life now, for our everyday life. It has a huge effect on astronauts on the space station, where they don't have the protection of the Earth's atmosphere. And if we're looking at, you know, sending people further afield, you can still get the effects of this space weather. It was just in the news this week, the aurora on the surface of Jupiter. You know, these flares don't just come to us because we're quite close to the sun. They spread very large distances throughout the whole solar system. So if we think about traveling to other places, Mars potentially, you know, in the very distant future, maybe some of the moons of Jupiter and Saturn, then we need to try and understand the dangers of space weather as well. Stars are a tiny aspect of what we look at in the universe. Our galaxy has 100,000 stars in it. 100,000. Our galaxy has 100 million stars in it, or billion stars in it, I should say. Some galaxies have a few million. Some are much bigger than the Milky Way. And we're just looking at that one single star compared to the Earth. Imagine a system of billions of those things moving around. So when we think about the numbers of things involved in astronomy, that's something that's quite unique, that you can be looking at, you know, the production of elements and particles within inside a supernova explosion, all the way up to studying cosmology, which is literally looking at the entire universe, hundreds of billions of galaxies, each containing hundreds of billions of stars. And it is something that we do need the observations for, because, you know, you can test as much as you want with maths and with theory and with simulations, but you have to prove those theories. They have to have testable predictions, and that's where it comes to looking at objects in space. And this is why telescopes are so important, because, you know, if you live in any city and you go and look at the night sky, you get the orange haze. You get the orange haze that comes with humanity, you know, us producing lights, having street lights, having shops, having neon signs, and it blocks out a lot of the faint objects that we can see. If you go somewhere dark, you might start to see a little bit more detail. You can start to see a few more stars. You might, if you're really lucky, start to see the band of the Milky Way, our own galaxy, stretching across the sky. But if we're just using our eyes, this is sort of the limit to what we can do. So you have to employ technology, employ a digital camera, even just something as simple as, well, what we think of as simple now as a digital camera. But because you can change the exposure on a camera, you can say, well, don't just look and process this information rapidly. Actually, just keep looking at this piece of sky for even a minute or a few minutes, and suddenly the sky looks entirely different. The Milky Band of our galaxy, you can start to resolve into individual stars, sometimes clusters of stars. You can see dark bands, which is not where there is a lack of stars within that Milky Way, but it's actually where there's so much dust that it blocks out the stars that behind it. You can start to see that the stars are not single colours. We see different colours in the stars, and that's giving you information. You can start to see gas, you know, those kind of red diffuse areas is hydrogen gas being emitted from some of these objects in space. So suddenly, by just incorporating technology into our understanding when we're observing the universe, you can start to pull out a lot more information. So telescopes and looking at the sky, trying to analyze the things that we see and interpret those things are a huge part of astronomy, and they help us in several ways. And there's telescopes that you can have on the ground, and we can start looking at, for instance, those red patches that we saw in the sky, looking at areas of star formation. So where a new star is being born, and they're always born inside these areas of cloud and gas and dust. But the advantage that we've also got is we have telescopes in space. So the difference between getting outside of our atmosphere and being able to analyze areas of the universe using space telescopes, even, you know, I said about Sophia, the aircraft with the telescope on it, so that flies at around 45,000 feet. So I don't know if anyone saw this weekend, you know, the Virgin Galactic space flight, they went up to 50,000 feet, which is like the lower definition of space. But just getting up that high can means that you're looking through so much less of our atmosphere, that the skies become so much clearer. There's less blurriness, there's less disturbance by our own atmosphere, and you can start to see all of these objects. Looking at these star-forming nebula is a key area of looking at, you know, what is the life cycle of a star? How do stars evolve? There's still unanswered questions here, you know. Stars don't, a cloud of gas doesn't just collapse down and produce one star. It collapses in pockets, it fragments, and it produces usually tens of thousands of stars from the same cloud of gas and dust. And those stars are produced in different masses. The universe, we're not entirely sure why, but the universe prefers to make low mass stars like our sun than it does to make high mass stars. So for every star like a massive star that will explode as a supernova, you'll get about 100 suns produced for the same. So these massive stars are rare, and we don't really understand the breakdown of why the universe prefers to, you know, make these low mass objects. There's obviously an impact of things like temperature and things, but it's not clear. And we have a relatively good understanding of the different processes that a star will go through during its lifetime. As a star like our sun will gradually run out of fuel, it will expand to become a red giant because it starts to try and burn fuel in the outer shells, which kind of puffs the star up and it expands. So when our sun gets to this point in about 4 billion years time, when it expands to become a red giant, it will pretty much encompass the Earth. So it will swallow up Mercury, it will swallow up Venus, and the Earth will be around the border of how big the sun will get as it's going through this part of its life. And then for most stars like the sun, they'll die quite gracefully. The core will collapse down, it will produce a white dwarf, and all of the extra material sort of just gets expelled into the universe. But that goes back into the next cloud of gas and dust, and it means that every generation of stars has elements in there that were created in the previous generation. So all of us have elements inside us that were only produced in the very first stars that existed in the universe. Anything heavier than helium and a little bit of lithium could only have been produced inside a star. So all of the materials that make up us, that make up the Earth, that make up our sun, were all part of this kind of cosmic recycling process produced from a former generation of stars. And the massive ones have much more spectacular endings. They'll turn into these supergiant stars, which is the same process as a normal star turning into a giant, but it can burn heavier and heavier elements until you get a very rapid cessation. I don't know what the right word is there. Cessation of fusion in the core. When you end up with iron being reached, it starts to cost you energy rather than create energy to do fusion above iron. So the core suddenly stops fusing, and all of the outward pressure that created stops, and the star collapses down. But because the core is now made of iron and it's very, very dense, the outer layers of the star that collapse down onto that core bounce back off, and it sends shockwaves through the star and it explodes the star. And all that gets left is this compressed core. And depending on how big that core was, you can create a neutron star, you can create a black hole. You might have heard of things called pulsars, which are rapidly spinning neutron stars, which have weird magnetic fields. And again, what's the difference? What makes a massive star explode as a supernova and produce either a neutron star or a pulsar? Where do those magnetic fields come from? Why do they not all produce the same thing? Where is the mass limit to producing a black hole? There's a huge number of unanswered questions there as well. So even though we sort of understand this process that a star goes through during its lifetime, there's still a lot of questions along the way. And then if we think about how we might observe these, this is a little video of the telescope that you've heard a bit about today, the Liverpool Telescope. So when it comes to the projects you'll all be doing this week, you'll be taking real data. You'll be looking at real data that's been taken from various telescopes around the world to actually try and answer a scientific question, and that's what we do all the time. You propose your scientific question, you submit it to the different telescope panels, and a group of people will assess how good your science is and how good that question is, and they'll decide if you can use the telescope. And on a normal telescope, the domes that you can see, around the rest of the site on La Palma, what will happen is they'll say, okay, yeah, your science question is good enough. We're happy for you to come use the telescope to try and answer that question. So you can come out between these 5 days in November this year, and you fly out to the telescope and you sit there. Well, you don't for the last 18 months, but normally you'd fly out to the telescope, you sit at the end of the telescope, and it might be cloudy for the entire 5 days that you're there, and you get no data, and you fly home again, and it's just, okay, try again next year. The difference with the Liverpool telescope is, because you don't have to be there, it does everything robotically. It can take all those observations itself, and if it's cloudy one night, it'll check the weather, it says, okay, it's not worth opening. I won't take any observations tonight, and then partway through the night it might become clear enough, it'll open up, it'll start taking observations, and it schedules everything itself. And without that, with no human intervention there, it does the process much more efficiently and much more quickly. So the other nice thing about the telescope is you're always pretty much guaranteed to get data back if you get time on the telescope. So yeah, this is a really important tool that we have, and that all astronomers rely on observational tools like the Liverpool telescope. So obviously we're biased, we love our telescope, so I have to show the little video there, but you have to utilise observatories all around the world. For one thing, one observatory site can't observe everything in space because you're restricted by what hemisphere you can see. So it doesn't matter whereabouts in the world you are, from any one position, you can only see a certain fraction of the sky. So it's important to get coverage in the northern and southern hemispheres. These are some of the telescopes some of the ones that I've used, not all of them. But this is probably the most famous set of telescopes right now. It's called the Very Large Telescope, because we're, as astronomers, you might learn this during the week, not creative at all in naming things. So the Very Large Telescope is a set of 4 all big telescopes. I can't remember if they're 8 or 10 meters in diameter, but there's 4 of them together and they'll work together. So you can essentially amplify the size of your telescope just by coordinating observations between them. And these sit in the Atacama Desert in Chile, which is one of the best observing, well, the best observing site in the world. And it's where the next enormous telescope is going to be built as well, which is called the Extremely Large Telescope. See, very large, extremely large, not good at naming. And that one is going to have a diameter of 39 meters. So just the mirror, just that one collecting area that you can see kind of on this telescope here, that is going to be 39 meters across. And every time we get these leaps in innovation in technology and engineering, it leads to a leap in our advancement of understanding of the universe. Every time something new comes along, we learn something new. So it's going to be really interesting to see that develop, because when we're thinking about, you know, things like exoplanets, things like looking at, you know, the difference in pulsars versus neutron stars and the intricacies of the magnetic fields and things, it's when you get these brand new telescopes and pieces of technology that you can really learn a lot. And then obviously we come out from stars, we get to the next scale up, which is galaxies. And our galaxy is the Milky Way. Our sun sits on a little spur from one of the main spiral arms. Actually, even understanding our own galaxies, well, it's much harder than understanding other galaxies in the universe, because we can't see it all. We sit within it. So just mapping our own galaxy has meant taking, you know, thousands, if not millions of observations of stars and very accurately trying to understand the positions of those stars and the movement of those stars, because galaxies don't sit there stationary. All of the stars within a galaxy will rotate around the core, or what we call the nucleus inside a galaxy. So actually just getting an understanding of our position in the universe helps us understand other objects in the universe. And measuring distance in astronomy is an enormously difficult task, because how do you know if an object is bright because it's big or it's bright because it's close? And disentangling those two things is a huge area of astronomy that we're still trying to get to grips with. So our galaxy is a fairly typical spiral galaxy. It's got a bar in the middle. Some spiral galaxies have bars, others don't. But there are many different kinds of galaxies. Spirals are one of the main types, but there's also elliptical galaxies, which don't look anywhere near as interesting. I'll show you a picture of one of those in a minute. But you get dwarf versions of galaxies as well. So you can get dwarf spiral galaxies, dwarf elliptical galaxies, which only have a few kind of million stars in them rather than billions. You can get galaxies. So this was the other thing that I studied for my research, was looking at galaxies that smashed into each other. So the galaxies are dynamic, they are rotating, they are moving, but also they're moving around in the universe. The universe itself, everything is moving, and galaxies can crash into each other actually quite frequently. And that's quite interesting, because that's exactly what's going to happen to our galaxy. So this is a simulation of the Milky Way. Oops, I think I've lost my, I can't do it on the screen. So the one on the left of the image is the Milky Way, and the other one is Andromeda Galaxy, which is our nearest big galaxy in the local neighborhood. And we know that ourselves and Andromeda are moving towards each other. And in around 4 to 5 billion years, our galaxies are actually going to collide. And it's not kind of as, if you were living on a planet orbiting one of these galaxies, it wouldn't be as dramatic as this looks, because there's a lot of empty space in galaxies. Even though there are billions, well, yeah, billions of stars in them, there's an awful lot of empty space between them. But it's quite interesting to think about how our galaxy is going to evolve, actually kind of serendipitously on the same sort of timescales as our sun is going to run out of fuel. We're actually going to start colliding with Andromeda as well. And we see different galaxies, different objects in space in various stages of these sorts of collisions. So we kind of have to essentially, you're kind of taking photos of lots of different things on different stages of that evolution and trying to work out how that evolution occurs. we have a couple of small satellite galaxies that orbit around the Milky Way, and they're called the Large and Small Magellanic Clouds, and you can see them from the southern hemisphere just in the night sky, just with your with your normal eye without using binoculars or anything. And we're pretty sure that those have already passed through the Milky Way once, and they're starting to rotate down. Eventually they'll collide and become part of the Milky Way as well. So there's an awful lot of kind of stuff moving in space that you have to try and understand as well. So dynamics, distances and dynamics are some of the key questions around astronomy. And the other thing that's so interesting about space is where you don't think there are questions, it gives you more questions. So the Hubble Space Telescope, probably a decade or so ago now, maybe even more, took one of the most kind of famous pictures in astronomy called the Hubble Deep Field. And what it did was it looked at a patch of space that looked like there was nothing in it. And it just stared at that patch of space for a really, really, really long time. And the image that came back was this. So that bit of space that looked like there was nothing in it was full of essentially galaxies. So this thing here is a star, and this thing here is a star. When you get these little spikes coming out, it's because the stars are bright enough because they're close that they saturate the camera, and you get what's called diffraction spikes. Everything else in this image, apart from that one, another spiky one, everything else in this image is a galaxy containing billions of stars. And this was in a patch of space that looked empty. And this is the thing with using telescopes, is if you stare at the bit of the sky for long enough, you allow all of that faint light to travel to the telescope and to hit the camera. And this is the kind of thing that can come back. And this is a zoom in of that called the ultra deep field. And you can see the different kinds of galaxies. You can see kind of spiral galaxies. You can see that some look kind of like blobs. They're elliptical galaxies. And you can see, if we take a little zoom in here, you can physically see the motion of these galaxies, just in taking these still images. You can see that these three galaxies, or what was probably more than that, because this looks like a dwarf galaxy that's collided with this one, they're interacting with each other, they're moving around. The universe can be quite chaotic, and trying to, understand that chaos. It's one thing simulating two big galaxies colliding with each other, but what if you've got an area of space where you've got 10 galaxies all colliding with each other? How does gravity work in that situation? How do the dynamics work in that situation? And if you want to extrapolate that, if you were living on a planet around one of these stars, what would that be like for you? So there's an enormous number of questions around that. And this was the interesting thing about this observation, was it allowed us to sort of weigh the universe in a sense, to try and get a handle on how many galaxies were in the universe. And this is how we know, we estimate, I should say, rather than know, that there are more stars in the universe than grains of sand on every beach and desert on planet Earth. So Sahara Desert, every beach, everywhere you want to look at for sand on Earth, think about the grains of sand that you could pick up just in your hand, and there are more stars in the universe than that. And I don't think it's coincidental that the maths for that was done by someone working in Hawaii at the telescopes there, because you get to chill on the beach all the time as well. But it gives you an idea about the scales involved in working on astronomy. So yeah, and this whole concept of asking questions and seeing what comes out, let's just stare at this blank piece of sky and see what's there. If we look at it for long enough, if we allow the light from these objects to actually hit the telescope, let's see what happens. And it unlocks an entirely different view about what the universe is and what it's composed of, and the motion in the universe, and looking at the early universe as well. Because the other quirk of astronomy is the more distant an object you look at, the further back in time you are looking, because the light from that object can only travel at the speed of light. It's got a finite speed, so it takes time to reach you here on Earth. So the longer it's taken the light to reach you, the more distant the object is, also the further back in time you're looking with it. So it's a sense, you get a handle on time travel as well. There's so far back in the universe that we can look just by taking observations of really distant objects, until we hit a black wall, which the earliest we can see back is something called the cosmic microwave background, and that's sort of these, you probably, if you've done any astro within your kind of physics A levels, heard a little bit about it, but it's this, you know, imprint of the Big Bang on the universe. The thing about that is it's essentially the first light that was produced, and it's the first light that we can see. And because we don't really have much way of observing the universe other than light, it provides sort of a brick wall that we can't see past that, because we don't know what signals to look for that weren't produced from photons through photons. Space telescopes are one of the biggest things that we've got for trying to probe a lot of the questions we've still got about the universe, because as big as a telescope can be on Earth, you're always still trying to compensate for the effects of the atmosphere. And there's ways we can do that, but you never get as good an observation as you can from looking at an object in space. And one of the telescopes that's going to come online soon, that I'm just going to play a little video of, is the, it's currently known as the Webb telescope. It may well change name before it gets launched, but it's the next kind of generation of space telescope. And this is a NASA kind of slightly cheesy video, but it's also quite interesting to tell you know what Webb is going to do, why it's such an interesting telescope, not just in terms of astronomy but in terms of engineering, and also what I think is one of the most exciting things about it is it's finally going to launch later this year. So currently looking at October this year for launch, and this project has been in the pipeline for 30 odd years. We've been waiting for the launch date for a very, very long time. So it's going to provide some really interesting results when it actually gets to its position in space, which is another interesting aspect of it.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope.
Sorry, how integral the relationship between the astrophysics and the sciences with the engineering and the technology. You know, the two absolutely go hand in hand, and it's this is an enormous feat of engineering. So it'd be really interesting to see if it all works to plan. The 3 weeks of it slowly kind of unraveling itself, but also this telescope is not going to be placed in orbit around the Earth like telescopes have been traditionally in the past. This telescope is going to a different orbit which sits between the Earth and Mars. It's called the Lagrange Point 2, and it's sort of a stable orbit traveling around the sun. So when this telescope gets there and starts kind of unfurling, we can't go and fix it. If anything goes wrong, that is it. That is, you know, 30, 40 years of planning, engineering. I can't even remember how much it costs so far. I think it's like of the order of $10 billion that this has cost so far, and that's without it actually, you know, going up in the rocket. So if anything happens, it's just lost. It's just lost. We can't ever go and fix it. We don't have the technology to get people there to fix it. So it's yeah, it's going to be really interesting to see if it works. So look out for this heading out at the end of this year, and the advancement it brings, because, you know, it wasn't an exaggeration in that video. It will lead to the advancement in our understanding of the universe, and every telescope that's gone up has helped to help us understand the universe in some way, shape or form, to the extent that we now have a handle on what the universe is at least made of. And the stuff that Webb will be able to see, the stuff that all of our traditional telescopes will be able to see, is like 4% of the universe in mass. The rest of the universe is held in dark matter and dark energy. And dark in astronomy doesn't just mean it doesn't produce light, it means we don't really understand what's going on. Dark matter, we think is particle based. It's some sort of particle that we can't observe. We know it interacts with gravity because that's how we've observed it, that's how we've seen it. But we call it non-baryonic because it doesn't interact with light. So it interacts with gravity, it doesn't interact with light. We're still getting to grips with what dark matter could be. And then the bulk of the universe is this thing called dark energy, which is some sort of unseen force, which is pushing the objects in the universe away from each other. It's essentially expanding the space between objects in the universe. So, I mean, it's too much to go into now. This, like, you know, this is decades worth of work, but these are some of the biggest unanswered questions in astronomy right now. What on earth is dark matter? What on earth is dark energy? And because astronomy traditionally has all been led by light, the things that we can see, it means that we've got a, you know, I've talked about a lot of the questions we've got left, but we at least have some understanding of that 4% of the universe we can see, but we are nowhere near getting to grips with the rest of it. And that's sort of one of the things that comes with that is looking at black holes. So we know that a black hole exists. These are actual observations of the center of our galaxy, and you can track the orbits of the stars around the center, and it's like they're orbiting something that can't be seen. So you know that there's got to be mass there. There has to be some sort of mass. This is a slightly kind of more elaborate simulation of the motions of these objects, and you can work out from the orbits of the different stars and the masses of the different stars how big this object in the middle of there must be, how big the object is that they're rotating around. And I can't remember off the top of my head. Andy might have to come in and say how big the supermassive black hole in the center of our galaxy is.
About 3 to 4 million times the mass of the sun.
Yeah. So the black holes you're producing from supernovae are of the order of, you know, 10 times the mass of the sun. So this is another huge question is, so we have black holes that are of the order of a few tens times the mass of the sun, and the supermassive ones that sit inside galaxies that are millions of times the mass of the sun. We don't see black holes really that sit in between those two mass ranges. So how can you get from these small ones to these enormous ones that sit in the middle of galaxies? This is an enormous unanswered question in astronomy. So looking at things that we can't see is one of the kind of new things that we're trying to do, or at least we can't see traditionally, one of the new things that we're trying to do with astronomy. So one of the ways we do that is through these simulations, and this is looking at this is quite a famous simulation in astrophysics and in cosmology called the Eagle simulation, and this is mapping the dark matter that we know about in the universe based on how it interacts gravitationally, as I've mentioned. So Rob Crane's one of the professors in our department, and he's been one of kind of the pioneers of doing these like high processing simulations, high computer powered simulations, trying to map the universe in this way. So we've got the simulations. What we need is the simulations to give us testable predictions that we can then go and observe to prove or disprove. Most of science is disproving theories rather than proving them, as you might know. So this is sort of the really early stages of us trying to get a handle on the stuff in the universe that we can't see with light. And another part of that has been looking at gravitational waves, which you probably heard in the news a few years ago now. Was it 2017 they were initially? We initially got the signals through from the first gravitational waves. So I love this. This is the signal from that was received from the telescopes here on Earth, trying to detect these gravitational waves, but with audio attached to it. So they've used the frequency of the vibrations in the instrumentation and placed that with audio. So that's the sound of two enormously dense objects in space colliding. It sounds quite peaceful when you actually think about what's going on underneath that noise. And the things that we know would be massive enough to produce enough energy to send these gravitational waves, these ripples in space-time, these vibrations that we can actually now measure. We're talking about black holes merging, we're talking about neutron stars merging, maybe white dwarfs, but probably not. Not that they don't merge and do stuff. We know that they merge and do stuff. They produce things called thermonuclear supernovae, which will help to measure distances in the universe. We don't know if they're big enough to produce gravitational waves along with that. They probably are, but our technology is not good enough to measure vibrations that small yet. So again, this is a new area of science, a new way to investigate the universe, not by just looking at light, not just looking at dark matter, but actually looking at these little perturbations in space-time as well, which is telling us things about things colliding in the universe, but not just things colliding, extremely massive things colliding. And what that means is it's a lot of energy. So we're looking at some of the most energetic things going on in the universe, but also trying to figure out a whole new way of observing that's not using light. So this is going to lead to a complete advancement in the things that we can do as well, as soon as we can you know, perfect doing these observations and perfect the technology. And again, it's probably going to mean trying to put one of these detectors in space rather than on Earth, because on Earth you get so much vibration from, you know, I mean, literally a truck going down the road near one of these observatory sites can cause a signal in the system. That's why you have at least 2 of them, so that in different parts of the planet, so that if they detect something at exactly the same time, you know, it's a source from space and not just something kind of in the local environment that's caused these vibrations. So you want to get rid of all those vibrations, you need to go into space. So there's plans for detectors like this to actually be put into space as well now. So yeah, an enormous number of unanswered questions, an enormous opportunity, I think, with some of the technology that's coming online, and gravitational waves and dark matter, and us starting to at least try and understand it a little more. That it means kind of the next, I think, 20 years in astronomy is going to be huge. And part of that is actually, yeah, the big questions, right? Where did the universe start? Where will it end? We sit in a time within our universe's life that it's very hard to distinguish between the different models for whether the universe is going to collapse back down on itself, whether it's going to expand more and more and more rapidly and eventually tear itself apart, or whether it's going to expand to a degree and then what we call become a flat universe. So the energy for the expansion just disappears, and it will just live forever at a certain size. So we're sort of still between these models. We think we're currently on the path for a flat universe. So the universe is currently expanding and accelerating, but eventually that acceleration will slow down and will just become a flat universe. But we don't know for sure. And this is like the really big scale of the questions on the universe, and the ones that everyone wants to know, right? Is there life in the universe? How will the universe end? How will the universe start? And those questions we still don't have a handle on. So that's why I find astronomy so interesting, is that there's still so much to answer.
I've been asked to do a session about thinking about PhD. So I will just say in advance, like all of you lot, I'm presenting from home, so I apologise in advance if the doorbell goes. My wife has a habit, I'm convinced, of ordering deliveries deliberately when I'm seen to be presenting. So hopefully that won't happen, at least because my son's at nursery, he's not going to run in and just say he needs a wee like he's done several times during these type of virtual talks. So it should be a little bit more professional compared to other ones. But just so you've got a bit of an idea, I did my degree in drama and English literature a long time ago, it feels now. I did a master's as well, just because I was a glutton for punishment and I really enjoyed the subject. But since I've graduated, I've worked obviously within a theatre, so connected to my degree, but then also it moves into admissions, student support, and now my normal day job is going up and down the country, speaking to students. We've done a tiny bit of that this year, but most of it's been virtual. It's just actually quite nice just to see cameras on and to actually see people's faces. And even somebody from the look of it is in a Star Destroyer from the look of it, so that's really good to kind of see. But generally what I was trying to say, I've pretty much heard it all, seen it all before, so if you do have any questions, do let me know. The best example that I still always say I ever got when I worked in admissions to university literally read, "Please take me on," and "please" was spelled PLZ. So nothing really does shock me anymore. And I have got a bit of an interactive quiz that I will launch in a moment or two, just so it's not me talking at you for the entire time. I'm not going to put any pressure on anybody, but if Emma does take part in that quiz, I'm expecting quite good results from her because she used to work in our team. So there's no pressure there. If she can't answer issues about university, there's something to, a conversation to have later there for you. Normally when I do these sessions in person, and I can, if you imagine you in a classroom, I can have a chat with you and stuff like that. The first question I ask is, what is a university? It's always interesting what different people's answers, but the official dictionary definition obviously is that educational institution in which, you know, you do academic degrees, research is done. And that's kind of the two models that you'll get. Some universities that focus a lot more on research, others will be more focused on the teaching, but there's a lot more than just the academic side, which I will touch upon a little bit later on as well. So the interesting thing will be, when it comes to that, what would you say are kind of reasons that people would go off to university? So if you want to put that into the chat, because the answers I'm going to show you in just a moment are taken from the student room. So they are genuine student answers. So what reasons would you maybe go off to university for? And as you're typing them in, basically what I would say is, if you think that, you know, university is the best thing for you, it should be a personal choice. So not, well, my mum and dad have told me that I have to go, or all my mates are going to that one institution or doing that course, so that's what I'm going to have to do. So at the end of the day, it's down to you as your personal choice. So you see some good ones there. Emma thinks the same way as me. Student discounts, that's what I tend to, you know, think about. Some ones do need a job, you know, you need a specific job for a degree. Step out your comfort zone, really good one. Meet different people, try new experiences. So some really good answers there. So you will see that some of those are reflected in actually what these ones from. So has anybody ever been on the student room before? A nod there for that. So the student room is, if you haven't been on it, it's a really good student forum. So there's GCSE, there's A-level BTECs, there's university students on there. So quite often, when they feel there's a bit of an issue, they will go on there and people can help each other out from all around the country. But equally, it means you get some really honest answers. So you'll see some of these are quite serious, a bit like maybe some of the answers that you've given. Others are maybe more personal reasons. So you'll see some of those ones there, like the grey one, you need a degree, you know, for a chosen career. Some of you mentioned that, you know, meet more earning power, career progression, moving away from home. I kind of fell into that orange bottom one, if I'm being really honest. I didn't have a clue what I was going to do. The careers advice I got was literally like, you're doing 2 really good A-levels, just do that at university. So hence my degree. So it gave me a chance to think about what I was going to end up doing. So the most random one, that yellow one, somebody saying, you get to wear fancy dress. Now, in almost 10 years of doing this job and going up and down the country, speaking to students, I've never had somebody say that to my face yet. The student nightlife, maybe that's an answer that I get, but never that specific. But it does just show you that on the student room, people will give you really good, honest, personal reasons. Now, when you kind of look at any of those top surveys that governments and stuff like that will tend to run, they're the answers. So earn more money, to pursue that vocation if you do it. If you're not too sure, study a subject that you enjoy. And literally some of the other universities I've been chatting to over the last week, they've been saying the transferable skills that you will get from any degree can lead you to nearly any kind of career that you want to. So, you know, if you're not sure what you want to do when you get to that stage, as long as you're enjoying it, the likelihood if you enjoy the subject, you're going to get good marks in it. Obviously, there's career opportunities. And just out of interest, if I change my camera, the screen view, out of interest, put your hands up. How many of you would consider moving away from home? There's a few hands, yeah. And it's one of those you genuinely find that, you know, when I do this in class, there's always someone's like, yes, straight away, how far can I possibly get as well? And I will show you how far you can move away in just a moment or two. There's loads of terminologies that universities will show at you. So most people will apply for an undergraduate degree, and that basically just means you're a graduate when you've completed it. So you're under that graduate level, so you're going for your first degree effectively. And typically that could be 3 years or maybe longer, depending on the subject you're doing. A foundation degree, there's normally 2 routes people will take. So for example, you might get some like people go, I don't feel I've got just enough expertise in that subject area. So like you might, sometimes you'll see art students go, I don't feel I've got the techniques enough. So I'll do a foundation degree that gets me up to that same standard. Equally, sometimes it might be if people took the wrong course, for example. So if you needed mathematics at A level to do a specific program, you didn't have enough of that, then you might get off the foundation degree. Or even sometimes if you just miss out on the grades, we'd offer the foundation route. You can equally study more than one subject as well. So like for my degree, the and signifies to an employer that it's a split 50-50. that I did both of them just as equally. So when you're going forward, it's important to think about, you know, well, what type of interests do you have? If you know what career you want to do, fantastic. Start exploring what courses might be best for them. If you don't know, don't worry too much about that. Still, the students in year 13 who are about to start university still probably don't fully know what they want to do with themselves. A sandwich course isn't a year of working, for example, in Subway and becoming an expert at how to make a butty, but it's where you actually get a year of paid work experience. So if you imagine like a computing student, for example, you'll take 2 years of the degree. Third year will be a year of placement, normally with like a reflective journal, so you're still getting assessed by the university. And then the fourth year is effectively year 3 of the standard degree. So when you go for a job interview, you are saying, yes, everybody else has the same degree result as me, but I've actually done the job for real. So I don't need as much training. I can just get on straight away. So you can imagine who's that bit more attractive. Study abroad, when obviously when the borders reopen and we know what countries are green and whatever it's going to be going forward, you know, hopefully that will return and students can go off and study in a different country, for example. Could be for a semester or a whole year. Sometimes you could gain a different qualification from the foreign institution, as well as obviously your degree. But equally, there's loads of opportunities to go abroad. So if people haven't already mentioned, John Moores has a little observatory over in Tenerife that people could go off to. So, you know, there's different opportunities within courses like that. An integrated master's as well is another terminology we like to say, and that's basically where you gain your master's degree alongside your undergraduate. So you normally would study for 1 extra year. So if you were doing a 3-year course, it would become a 4-year degree. And then when you graduate, you've got your master's, you've got your undergraduate. It's a slightly cheaper way of getting a master's degree if you could do that. And again, from an employer's point of view, it says that you've taken a lot of time and focus on your own education. You're a little bit more specialized than maybe other people who are applying for that job. But equally, you can then turn around and say, if I put that much care and attention to my own education, imagine how much care and attention I'm going to put into your job. And then a new, still up and coming one, but very competitive is degree apprenticeships. So degree apprenticeship is where you find a higher level apprenticeship. And basically all large companies pay a tax into this apprenticeship levy. And then the government uses that to pay for things like degree apprenticeships and standard ones. So if you were successful in getting onto that, you'd apply directly to a company, and then you effectively get on day release to a university. Day release makes it sound a lot worse than it is, but it's normally like you'll do 1 day a week, or you might be doing, you have a few weeks where you don't go to university, and then you might do like an intensive week on site. Typically takes a little bit longer, 5 years, because it's more spread out, but you don't get a tuition fee because the government is using that tax to pay for it. You don't get a maintenance loan because you are got a standard living cost. So effectively, you're gaining your degree, but you've got a full-time job at the same time. So that attractiveness is why it's super competitive. So if you ever are considering that, the earlier you start looking at degree apprenticeships, the stronger chance you've got of getting onto one. Equally, because you apply directly to your company and then the universities, you could technically not cheat the system, but you get more options. So if you imagine you are doing something in a specific subject area, you could apply for 5 university courses, but you could apply for as many degree apprenticeships as well. If you've got a degree apprenticeship, you just say bye-bye to your UCAS application. If you don't get a degree apprenticeship, you've still got 5 really good options that you could say, well, I'll go to university and get a degree that way then. So loads of people will say there's different reasons. This one is a little bit more subjective in some ways, but why people choose their specific university. So the last question that I will put on the quiz is, why do you think people choose their specific university? So if you imagine, why did some people pick John Moores over the University of Liverpool, or Man Met over Manchester? So the facilities, course choice, accommodation, or student support services. And this obviously takes in more an average of what people say, because it does differ depending on what your priorities are realistically. So people have got about 5 seconds left there. People taking more time to think about that one. So interesting, people say facilities and course choice. Accommodation next, student support kind of going down. Course choice is generally the top answer that people tend to give you. And that's partly the module breakdown, make sure it's the right course for you. Equally, just making sure the university offers the correct degree for you. Even little things like the the slight detail will make a big difference. So people say geography is either science, some people say, some will say it's a humanities, and it could be either or. But if you're a sciencey person, you apply, for example, for a BA geography, you're not going to enjoy it as much. So I'll go through a bit about them. I will come back to that quiz, so I will keep that there, so you will see the results at the end. So I would leave it in suspense. It's dramatic irony. You can tell that I did a drama degree, can't you? So when you do look at it, look at those module breakdowns for course choice. Really make sure it's offered. Don't do what somebody once did. So when I worked at Liverpool Hope University, which is another smaller campus-based university in the city, doesn't do nursing, and I'm there at the open day going, hello, what can I do for you? Where have you come from? What courses are you here? And this person went, I've come from Kent and I'm here to see your nursing courses. So they'd got Hope and John Moores mixed up. So really awkward to say, oh yeah, you've got the wrong university. So definitely make sure you look at the course choice in that sense. When it does come to facilities, my job realistically, I would say my job is to make sure you get to the right destination. If it comes to John Moores, that's amazing. If you go to another university, as long as that's the best choice for you, that's the best thing for you. But you'll get some people who obviously will go, my university is better than all the rest. Have you looked at all these nice pictures? If you picked up one of my guides, everything is looking amazing. Everybody is smiling. It's always sunny in Liverpool as well. So you can imagine how realistic those pictures are, but they're designed to make you go, we're the best institution, come to us, you're going to be one of these happy students. And you can make anything look amazing. So when open days can happen, it's really important that you actually go round and look at a university you're considering. So you can partly speak to the students and make sure they're getting paid, not just to be like, yes, you're going to love this course just as much as I do. And you can see that genuine passion from them. But equally, you can go around those facilities, see, do they match up to your expectations? Are they as big as the pictures make out? And ask the question, how often do you get to use them? I worked at a previous place that would said, took you around the robotics suite. It looks amazing. Then when the students started, they went, oh, no. You don't get to use that facility. That's for the PhD students. You use that one in the old building at the back. So kind of mis-selling it. So at least that way, when you go to the place, you know what you're getting yourself into. Equally, double check what the entry requirements. So if you know you need to get specific course, A-levels or BTEC in advance, you know you can get onto them. Also be seeing, is there any work experience that you might need to be talking about? And look at different reputational things. So the student room I've mentioned already. There's the REF, which is the research quality. So loads of universities might say, oh, we're really good at this in the REF. Some might talk about teaching quality. Again, it's different terminologies that they will say, I'm better than them type thing. The league tables as well are really good, but they all use different metrics. So you could be, for example, a university in the top 50 in the Guardian, but you might be like 80th or 90th in the complete guide. And equally, if you are looking at league tables, look at the subjects. Because certainly I know, just because I've just literally had a conversation with mathematics, we're probably, John Moores at the moment is about 70th in the league tables, but maths is 5th in the country. So you might get some students who go, I'm not considering that as a university because it's so low down, maybe in a league table. But for subjects wise, it's one of the best. So it's worth, again, always taking things with a pinch of salt, looking what's best for you. And when it comes to that location, think about how far do you want to go. So some students might go, I want to move away from home, but be like in that 2-hour travel radius. Others, it's like, so if I was based in Liverpool, Inverness, Cornwall, it's as far away as I could possibly get. Equally, if you are going to commute, how long would that take you? So I wasn't allowed accommodation at one of my uni options because I lived within a 30-mile radius. So because of that, it was going to take 2 hours of travel to get there. 2 hours of travel to get back. I wasn't going to get any of that kind of student nightlife experience. So in the end, that's why I said no to that choice. And the same when it comes to accommodation as the university facilities, you will get shown loads of great pictures of accommodations when you come to apply. And look, this one's got a swimming pool, or this one's got an inbuilt cinema room and all stuff like that. But at the end of the day, you're going to be the one who's spending a lot of time in there. So make sure it's something that's good for you. You can save a bit of money and maybe get a shared facility room. Maybe that's got a slightly longer walk to get to your building. Others will be going, no, I'm paying top whack to make sure I've got an ensuite and I can roll out of bed and I'm in my lecture theatre. So again, it's all these personal choices. And the support services is a key one. And obviously, they're the ones that we call them, but different universities will have the exact same teams and we'll call it all different stuff. And you might not even think you need some of those support services when you start university. I never needed disability support because I wasn't considered I had to have a disability when I started uni. It was only during the final year of my degree that I was living with trainee teachers who went, do you know you're ticking all the boxes for dyslexia and we're getting trained to spot that at the moment? So I got a load of support just for the last 3 months of my course when I got that diagnosis. But money support, and most importantly, careers and jobs. What can an institution do to get you onto that graduate level job? But it is about getting that balance right, and it isn't all just about the academic study, because if you were to just study and study and study all the time, you'd burn out. And if you burn out, you're not going to get as good of grades. So you do need to let your hair down from time to time. So be thinking about all the other different type of things. So a city-based university, everything's pretty much all spread out across the city centre. So we'll get people coming to Liverpool. So there's 50,000 students coming to the city across all the universities, and they're coming because the nightlife, it caters for it, the amount of different museums, art galleries, for example. But for other people, a city might be far too big. So a campus-based institution might be better for them. So you can see here, for example, it can be quite a large campus, but everything's relatively in one place. Now you can get different things. So for example, we would say we've got 2 campuses within the city because we've got them at 2 different points. The University of Liverpool is spread out across the top of the city centre. So they count as in some ways as a campus city university. But then equally, you'll have some that maybe might be out in the suburbs, some might be out in the middle of the countryside. So again, there's loads of options to kind of see what would be best for you. And obviously you're not at that stage yet, but I always think it's important to think about when it comes to it, what type of things would we be looking for? And I generally say to like the year 12s, what 3 things would you would say about yourself now? What are you really proud of achieving, and what type of things would you expect me to ask you in an interview? Because realistically, we're always looking for, yes, are you likely to accept an offer and contribute to the course, but all those transferable skills. And people really struggle with actually saying what I'm really good at, because we don't want to appear big-headed. And certainly the year 12s, year 13s that I speak to, they can't answer those questions. And it's really important you start recognizing your skill sets from an early stage. So even little things, if you think they're independent study skills, time management skills, the pandemic's not given us many positives that we can take out from the last 18 months, but something that you should all be really proud of. The fact that you're taking part in something like this says a lot about your character. You have shown more resilience, adaptability, independent studies because you've been sent home, and time management skills than any student your age, say from 2 years ago. No one's gone through this. So you've got this skill set far more developed than what any other cohort has before you. And you may not think you've got it, but the fact that you're doing something like this speaks volumes. So definitely make sure that you upsell yourself. And everything that you should always do, no matter if you're applying for a job or a course, for example, it should be backing it up. So what's the activity? How does it benefit you? And how do you relate that to your course? So as a quick example, just out of interest, how many of you put your hands up would say you've got or had a position of responsibility? Okay, 1, 2. Okay, out of interest, how many of you have said you've done any babysitting? So it's always interesting if you get more people kind of say stuff for babysitting. Now, it sounds really daft. The only people that have looked after my 4-year-old son is my parents and my in-laws, because they've got a vested interest in saying he's alive when I get back. And it sounds daft, but that's what I'm asking them to do. In the first lockdown, I caught my son when he was 3, pulling the chair from the kitchen table over to the side cabinet, because he knew he could climb onto the chair, climb onto the cabinet and open the cupboard with the biscuits in. Now, obviously, if he was left unsupervised, he could fall and, you know, the worst could have happened. So that's why you need someone to look after him. So by asking people, I'm putting a lot of trust, a lot of responsibility onto them. So if you've done any things like babysitting, you quite often go, well, it's for my brother or my sister. It's not that big a deal, really, is it? It is a massive deal. It says a lot about your character. It says that you can do all these extra responsibilities on top of your current schoolwork as well. So from my point of view, you could do that, then you could probably join a club and a society or get a part-time job and complete your degree. If it's for a job, it shows you can manage your time effectively and stuff like that as well. But when it does come to the student life, there's loads of courses you can apply for. Typically, students have got 8 to 15 hours worth of contact time with a tutor. That does vary depending on what degree course it is. And obviously, the contact time starts off higher in your first year, reduces more when you do more independent learning. those lectures, it's almost like saying being in the cinema or theatre where you're just looking down on somebody. And the interesting thing going forward is what some universities will have adapted from lockdown. So I know a lot of students have said, as much as they know that virtual had to be the only way, what they did like from the virtual ones is being able to rewatch lectures over and over again. So if you didn't understand it, you could rewatch it. So you're starting to see more universities saying now, well, we might actually go back to face-to-face lectures, but we're still going to record them, and so we'll be able to see them at any time. So it's interesting how the sector's going to change. Seminars are going to be more like your school classes, smaller numbers, maybe 20 to 40 people, depending on the university. Then tutorials are smaller group sizes, so about 10 to 15 people maybe. So certainly there was times when I felt too thick to say in a lecture, I have no idea what you're talking about. Can you give into more detail? But in front of 10 odd people, I could say I had no idea what went on in that lecture. But quite often you'll find everybody else goes, thank God you asked that question, because we had no idea neither what they were going on about. But that independent study of skills, it does mean you can study when you want. So my cousin decided to get up, she'd go and have a nap, then she'd get up, go to the library at 1 o'clock in the morning when it was nice and quiet and do loads of work. I could not do that at all. I was very much like, finish my classes, come home, do the work that was relevant, and then I've got the rest of the night just to relax. So again, it's set about your workloads, and it's setting you up realistically for you having a full-time job. How do you manage your time effectively? What environment would you work best in? Equally, do you get all those long summers and so that? So a lot of students will go off and do traveling and things. And like Emma said at the very start, there's student discounts. You know, whether that's 10% off a pizza, there's the Freshers Fair that I love to do. I still go around Freshers Fair just to do market research, and I just get the free sweets and the pizzas. I think I've still got 2 spatulas from my Freshers Fair because I just kept going around and getting all the freebies. My wife's only managed to set fire to 2 of them so far, so, you know, we've got 50% left. But there's loads of random opportunities that you will get. Equally, be thinking about, you know, if you were to go to university, is there a particular sport or passion that you follow? So you'll get students who will come to Liverpool, for example, who will get a job at Liverpool Football Club just so they can watch their team. I do have to say, like a BBC unbiased, there are 2 other teams based in Liverpool, but we won't name those ones. But equally, there's stuff like, for example, there's cricket, there's the horse racing, there's golf that people might come for to Liverpool. Equally, there's all those extracurricular activities. So I mentioned about going abroad. Loads of different universities will have different pots of money that will support you going abroad and that as well, extracurricular. So this was a student who was interested in history. She applied for a pot of money, got to go off to South America. We'll have wildlife students go off and work in Borneo with the orangutans, business students going off and looking at New York and how that operates. So again, it's not just about the academic course, it's about all the extra things that will make you stand out. If you imagine in your normal classroom, you would all be roughly similar age, all from a similar background. What would make you stand out applying for a position just from your standard school class? If you imagine from an international playing field, anything then you can do that says, this is why I've got so many great skills, is obviously going to run in your favour. And again, think of things like culture. So what other type of activities you can do? So one of the things we're proud of, we've got more museums and art galleries and theatres and concert halls than any other city outside of London. So again, it's something for people to get involved in. People might use their university as a base as well. So quite often you'll see students from Liverpool that will go off, you know, if they come from Cornwall, they'll go up to the lakes, they'll go to Blackpool, they'll go to North Wales, over to Manchester and Yorkshire, because it's cheaper for them to do it from there than it would be from their hometowns. So again, you can plan these different activities in. I did mention accommodation. Obviously, remember these, I thought I'd show you some more examples. They're always meant to make you go, God, that looks great. I can't wait to move into them. So always make sure it is something that you will be comfortable with, and check how close it is. Some accommodation from certain universities, it could be 5-10 miles away from actually the city centre where you're getting taught. So is the buses available, and how easy would it be to get there? So one thing obviously that I've, you know, if you don't have no idea what you can do as a career, this is a free careers quiz that we have helped build with SACU. So you don't have to do this now, but this is something you can go away. I will put the link into the chat a little bit shortly. But how it works is you basically register through there, you get a confirmation email, and once you click on that, you're good to go. Click on the careers quiz, and you do 40 odd rounds of pictures like this. So you might just go, oh, you're meant to go, that one's me, that one's me. So if you imagine these ones, sporty, climbing the careers ladder, reading books, arty, I'd be the book one. Then you keep going through all these different rounds, it changes the metrics. Sometimes it might show you the same picture, but obviously with different ones around it, so it can gauge what you're doing. And the whole point of that is, afterwards you will get 3 results clouds. So this is my degree cloud. You get a careers one, and you get one on apprenticeships as well. So the whole idea is it's matching degree programs based on what you would be interested in. If you think about my degree, drama and English, 2 of the most prominent ones there. The amount of teachers that all come back saying you should be a teacher for their job one, so it gets them spot on. But it will also show you loads of random other ones that are out there as well to give you some thoughts. So you might go, I didn't know that was a real degree. What do I do? Or I've never heard of that job. What type of breakdown, what type of duties would you do? What salary could you gain? And that's roughly how it would look down for you once you got those results. So you could see degree programs, staff student ratio, satisfaction, how much money people typically earn afterwards. The bottom one there was those different job ones. That's just one free careers tool that you could use. There's loads of other ones out there, and the more things that you do to give you a bit of an idea will ultimately make it stronger for you. Other ways that you can do a bit of research, UK University Search had a virtual event this week that was now on demand. So that's what a stand looks like. There's no staff you can speak to, but you can go on there. There's loads of universities, you can go off and download a load of information from it. UCAS equally had a virtual Discovery Week a couple of weeks ago, and that's on demand. So there's a loads of really good websites they put together that you can go look at. Uni Taster Days is a really good kind of one-stop shop of different institutions. So I'll put, for example, the summer school that we've been running, that was advertised on there. Once we know more taster sessions, they'll go on. Some of them going forward will be virtual, some of them might be in person, but again, it's a good way of gaining different insights, different subjects or universities. And equally, there's the good old-fashioned open days that you can go off and look at as well.